Assalamualaikum and hi everyone. Today we're going to learn about fixed bias configuration for the small signal analysis. Before we proceed, I hope you have better understanding on Ohm's law, KVL and also BJT DC biasings. Okay, in this video we're going to learn about the fixed bias and also emitter bias configuration for the bypass. Okay, what is the difference between bypass and unbypass? For the bypass, we have the capacitor here. For the unbypass, we do not have the capacitor here. So what is the effect? We're going to learn it later. Okay, first for the equivalent circuits, we have to ground the DC sources. So we can draw this one as a ground and this one also a ground. And then this one we just ignore because this is just a short circuit, and also this one we just ignore the existing of the capacitor. So if we rearrange the circuits, we will have the configuration like this, where the base terminal from the base terminals is going to connect to the RB is here. From base terminal going to connect to RB, and then from the RB go straight to the ground. Okay, from the RB straight to the ground, and then for the E terminal there is nothing here, so it is just go straight to the ground. Okay, same here, straight to the ground, and then from the C terminal is going to connect to the RC, and then from the RC is connect to the ground. Okay, from the C, and then we go to RC and then connect to ground. Okay, this is the complete equivalent circuit yet. So if you still remember during the introductions, this one represent the transistor. Okay, the internal resistance of transistor, and also there another internal resistance between C and E junction. Okay, for the B junction or B terminal, we can refer here from the B terminal here is connect to the resistor RB, and then from the resistor RB is connect to the ground, and then from the E terminal is connect direct to the ground. So this E terminal is connect to the ground, and then for the C terminal it will connect to RC and then go straight to the ground. So from here we have the resistor RC, and then we have the ground. Okay, this one just for the output, if we want to measure the output voltage. So this is the output voltage here, I just draw. And then from the base terminal just now we have this point. So from this point also we can measure the input voltage. So I will label this one as a VI. Okay, so from here we can measure the Zin. Okay, same as this one, and then this from here also we can measure the value of Z out, the input and output resistor. So how to find the value of Zin? If you look from here, okay, if you look from left to the right, we can find out that RB here is in parallel. Zin will equal to RB parallel with beta RE. Okay, to calculate this one, I hope you can know how to calculate the parallel resistor. Okay, this is the total resistance, RB times beta RE, and then RB plus with beta RE. Okay, this is the Zin. Okay, I can say this is the input side. Okay, and then this another side here, we can analyze it separately. This one will be the output impedance. Okay, if you look here from right to the left, this one, so from this point we have parallel of two resistors, which is R0 and also RC. So Z naught is equal to RC parallel with R naught. So it's going to be the same way to calculate the total resistance. RC R naught over RC plus R naught. Okay, this is the input and output impedance. And then how to find the voltage gain? Okay, you have to remember this equation, which is voltage gain we note as a AV is equal to V naught over V in. Okay, and then we have to find the value of V naught. Okay, we have to find the value of V naught first. So the value of V naught, if you look from here, the current here flow from, if we look from here, it flow from bottom, right, here, from here to here, this current. So meaning that V naught is equal to, we have to use the Ohm's law, current times the impedance. So the current here is beta IB. Okay, it's minus because of the different polarity here. Okay, plus and minus, so that's why this minus. Beta IB times with the total impedance. Okay, the total impedance actually we already calculated here is equal to RC parallel with R naught. Okay, I just noted here as a RC parallel with R naught. Okay, this is a V naught. Okay, so value here is beta IB times with RC parallel with R naught. Okay, and then we have to find the value of V in. Okay, if you look here, I in is not given here, so we cannot use I in times with the total impedance here. So what we can do is we can find the parallel voltage of V in. Okay, V in is parallel with VRB and also parallel with beta RE. Since we do not have the voltage, the current here, the current flow here, we cannot find the voltage here. Okay, but we can find the total voltage here because of we have the value of IB and also we have the value of beta RE here. So this is positive, this is minus, so the polarity between V in and voltage here is same, so it should be positive. So here we will have the IB times with beta RE. Okay, so we have the value of V in equal to IB beta RE. Okay, and then just substitute the value of V naught and also V in into these equations. So you will find that the value of current voltage gain is equal to beta IB RC parallel with R naught over IB beta RE. And then just cancel out beta and also cancel out the IB. And then we can find the value of AV is equal to minus RC parallel with R naught over RE. But sometimes the value of R naught is equal to infinity. Okay, what happens if R naught equal to infinity? Meaning that you can ignore the existing of R naught. So if you ignore the existing of R naught, actually here is open circuit because this is very big, extremely big, so we can ignore. So meaning that Z naught is equal to RC if R naught equal to infinity. So this, so just substitute the value here which is instead of RC parallel with R0, it's going to be only RC. So this equation will be minus RC over RE. Okay, for the current gain, the equation is, the notation we will use the AI, and then the equation is I naught over I in. So the value of I naught, actually we can use the Ohm's law, which is I naught equal to V naught over Z naught, and then V naught just now we calculate as beta B times with the Z naught, which is RC parallel with R naught, and then for the Z naught we have RC parallel with R naught. This one actually equal to minus beta IB. And then for the I in, we can use the same law, which is Ohm's law, V in over Z in equal to Z in just now, V in just now we calculate as IB times beta RE. Then for the Z in is RB parallel with beta RE. And then just substitute this value into this equation, and then we'll find the equations. The equation is quite complex, but actually when you substitute the value, which is you calculate, and then it's going to be simple. Okay, I will just do the equation here. So AI will equal to beta IB with the minus over IB beta RE over RB parallel with beta RE. Okay, actually you can cancel out this one, cancel out with this one, and the IB cancel out with this one, and then the value of AI or current gain is equal to minus RB parallel with beta RE over RE. Okay, and then for the phase relationship, so if you calculate phase bias configuration, the AV is 100. So let's say the value here is 5 volt, and then once you amplify the signal, it's going to be minus 500. Okay, the phase is, I can say, is inverted. Okay, and then for the emitter bias, actually is same with the phase bias regression. Why? In AC analysis, what happened to the capacitor is short circuit. So the signal will go to the short circuit path rather than the resistor. So meaning that here the current will not, or the signal will not flow here, meaning that we will have this configuration. Okay, this is the phase bias configuration. So meaning that all the process, all the analysis for emitter bias configurations for the bypass is totally same with the phase bias configuration. What's next? I hope you do a lot of example in electronic device and circuit theory, and then please watch my next video on voltage divider bias configurations bypass. That's all. Thank you for listening.